All right, guys. So one example I asked you guys to try this out already. What equation do we need to use to do this example?
The F equals GM over R squared.
1m or 2? GMM over R squared, right? So I draw a little picture that kind of shows the example. Maybe you want to draw this on your notes if you can. All right, it's not a very difficult picture. Now, last hour they got mad at me because I didn't draw the ground flat. Okay? Why didn't I draw the ground flat?
Because
it's flat.
Because it's circular.
The Earth is a sphere, right? So if I drew the ground flat, then a lot of you would say, "Oh, radius is 1 meter," which some of you did, didn't you? Okay. The biggest misconception on a problem like this one is with the radius. All right. We forget to add the radius of the Earth. So, Skylar, let's say we're talking about another problem where we're talking about a satellite that's orbiting at 400 meters above the surface of the Earth. What's the radius?
6.400 meters times 10 to the 6th power plus 400.
There you go. You got to add the radius to the radius of the Earth. So don't forget to do that. All right. So you guys use this equation: F equals GMM over R squared. Now we have a big M and a little m right there, right?
Sure.
What's the big M?
The Earth.
The Earth. What's the little m?
The Earth.
The 2 kilogram object. So up here I have 2. If you read along earlier or later, they talk about 3, 1, and m, and we'll get to that in a second too. But the m, the big M, is the mass of the Earth, right? Right? Okay. The little m is what? 2 kilogram mass, right? Right? And the radius is going to be this, 6.38 times 10 to the 6th plus 1. All right? Now I'm going to leave the little m out here for a second. And you'll see why in a moment. Okay, so 6.67 times 10 to the negative 11 times 5.97. What was that, Rex?
What?
What'd you say?
I said you're the big M, always leaving the little M's on.
Oh, no. I want to consider myself the little m.
Isn't it little M too?
Yeah, we'll get there.
Oh my
Okay. So, there's the equation. Now, I left the little m out because we are going to calculate this force, not just for the 2 kilogram mass, but for 3, 1, and little m. Okay? So when you did this, you probably plugged in a 2 for m, didn't you? Yeah. So when we do this calculation, we plug in a 2 for m, we get a force. I'm going to write it over here. So F sub 2. Okay? The force on 2, what does that equal? 19.57? You guys agree with that? 19.57?
Well, you wrote it up there, so
Yeah.
I don't know.
Yeah? Yeah? Okay. And that's newtons, right?
Yeah.
Okay. So that's the force on 2. Okay. Which way is that force directed? Which way? Down. So if I were to drop 2, it would fall this way, right? Because it's the force of gravity. Does that make sense?
Yes.
So now this is the force of gravity on the 2 kilogram mass.
It is.
Okay. Now a very famous scientist did a similar experiment to what I've drawn up here. He took objects of different masses and he dropped them off of a tower that leaned.
The Leaning Tower of Pisa.
Good, the Leaning Tower of Pisa. Last time I thought it was the Leaning Tower of Pizza. Okay. The Leaning Tower of Pisa. Who's the
Mandela.
who's it?
Was that right?
What'd you say? No, it's not Mandela. Okay. What was that, Jose? Galileo. What was Galileo's conclusion?
He went to jail.
everything went to Earth.
Okay. Everything accelerated at the same rate. So if you have a 1 kilogram mass and a 5 kilogram mass, he dropped them both. They hit the ground at the same time because they all accelerate at the same acceleration. Okay. Now, what was the misconception there?
A bigger object.
Okay.
They thought
Big-
a bigger object
big-
would fall faster.
Good. Bigger objects fall faster. So in this case, we are looking at 4 different masses. Some heavier than others. Right? What I'm going to show you, what we're going to prove today, is if Galileo's observation was correct or not.
Didn't we do this before?
We did this experimentally. Right? Now we're going to do it with Rex's favorite word,
We know
theoretically.
We know it's true,
Okay.
though.
Okay. We're going to prove it theoretically, though.
But we already know.
Okay, well, I know you know it's true, but I want to show you why. Because what Galileo did 400 years ago, okay, can be proven true with what we're working on right now. And I think that's kind of important for us to know that. Can be proven true.
We already
Okay.
used
I know he didn't have calculators. All right. So the force on 2, the force on 2 is 19.57, right?
Yeah.
Okay. So now that's F equals gmm over r squared. What's the only force acting on this 2 kilogram mass though? Gravity, right? So what does Newton's second law tell me? Amanda, you got a question?
Yeah, I have a question.
What's that?
So why is it that a feather drops slower than
Air
a bowling
resistance.
ball?
Air resistance. Yep.
Oh, okay.
That's why
so
paper-
if like we minus air resistance and drop the feather in a bowling ball, they don't fall.
Yep. If we sucked all the air out of this room, we'd all have to hold our breath. But if we dropped a bowling ball on a feather, then it counts. Okay. So does that make sense?
Yeah.
Okay.
Can we do that?
All right. And part of it too. No, we can't. Part of it too is that the feather is so light that any little force will change the acceleration. The bowling ball has such a big mass that even little forces from air resistance won't change the acceleration that much. Okay, does that make sense?
Yeah.
Okay.
So like when in the cartoons, they're just like faking when like two things fall off and like the bird will still be like falling and
Yeah. Cartoons don't always get it right. All right. So this is the only force acting on this object, right? So how can we figure out the acceleration of it? F net equals ma. Newton's second law. I got the bad marker. Okay. So F net equals ma.
Why still a bad marker?
Because it's still usable.
Then why don't you use it?
That's not right. Okay, we're dark. All right. So F net equals ma, right? So in this case, the only force acting on the 2 kilogram mass is Fg, right? So Fg equals ma. If I want to figure out the acceleration, of this mass, what should I do? No, don't sleep.
Plug in the stuff and do the algebra.
Okay. But I want to make an equation I can use multiple times. So what would I do here to find acceleration?
Plug in the stuff and do the algebra.
No. I want to make an equation for acceleration. What do I do?
Make an equation for acceleration.
Divide by m. Now is this m the little m or the big M? The little m, because the big M isn't moving, right? The little m is accelerating, the big M is not. Right? Does that make sense?
Yeah.
So this little m, this m right here is the little m. It's a 2 kilogram mass. So we'll make a little note of this. So we have Fg over m equals a, and this is the little mass. Okay? That's the little guy. Don't like how I wrote that. Little.
Okay.
Yeah.
Okay, then why over there are they the same?
With the 1 kilogram stuff?
Yeah.
We already went through that.
No, why are they the same here, but
Well, why are the masses the same?
no, because one is bigger, but the other is just.
Because I first calculated the G using 2 1 kilogram masses to figure out what the force would be, and then added another one.
So would the 1 kilogram still be accelerating towards the 2?
No, they both accelerate at the same rate. This one they both have the same force. This one have a bigger acceleration because it's a small mass. Okay. All right, does that make sense? Yeah. Okay. So back to this. So how can we find the acceleration of object 2? What do I do to this number? Divide it by what? Divide by 2, right? Does that make sense, guys? So I take this 19.57 and we divide it by 2, and that will give us our acceleration. Okay. Did anybody get to that in the warm-up? Yeah, what'd you get, 9.78. Interesting.
Okay, 9.785.
Okay. What does that round to?
9.79.
9.79. What it was? If I want to keep one decimal place, what does that round to?
9.8.
9.8. So you mean to tell me the acceleration due to gravity of this 2 kilogram mass is 9.8 meters per second squared?
Well,
Interesting. So not only did you guys do that experimentally, but now we are doing this using Newton's law of universal gravitation. Right? Using Newton's law of universal gravitation. We are getting the same acceleration that we were told acceleration due to gravity was earlier in the year before we even knew about this. And I think that's kind of cool. That's just okay. Anthony, you right? Okay. Eric, pay attention up here, please. Okay, put your bag on the floor.
equation you used for the last
Thank you. What?
What equation did you use to find the last one you just did?
We did this. Force of gravity divided by the mass.
Oh.
Okay? So, that works for the 2 kilogram mass, right? Let's try the 3 kilogram mass. So you take this equation, instead of 2, what do we put in here?
Right.
3. So calculate that. Plug in 3 instead of 2 for mass.
Wanna be the same?
No, we're trying to find the force. This is the force equation. The force will not be the same.
I didn't know what we were doing.
Yeah,
Okay.
of course the force is different between the
3, right?
Yep. Second comma.
Whoa.
What do we get for our force?
Hold on.
29.35.
29.35. So the bigger mass experiences the bigger force. Does that agree with what we learned earlier?
It does.
Yeah, because the force of gravity we learned earlier was mg, so mass did affect it. Okay. What happens to acceleration? Is it bigger?
No. Basically the same.
Okay. So we take, to find the acceleration, we do 29.3 newtons divided by 3, which is 29.35, sorry. And what do you get?
9.78.
9.78. So, a 2 kilogram mass and a 3 kilogram mass have the same acceleration.
Oh wow.
That's crazy.
Somebody's done this before.
I know.
Witchcraft.
Okay. So,
Make it some water.
yeah, it's fine. Let's try the 1 kilogram mass now. Give the 1 kilogram mass a shot. Plug in 1 for m. What is it?
9.78.
Plug in 1 for m. What do we get?
9.78
9.78.
meters per second squared.
Nope. Okay. If you plug in 1 right here, you do get 9.78. Now, some of you might say, whoa, that's our acceleration. How do we get that for our force?
You only divided by 1.
Because we only have 1, right? The mass is only 1. So if I divide 9.78 by 1, what do we get? 9.78 divided by 1, what do we get? 9.78. So, guys, what have we just shown here? To some extent, we proved Galileo correct. That objects of the same objects of different masses have the same acceleration.
Is it weird that we have one in this?
Yes, Rex, because remember earlier I beat it in your, I shouldn't say beat it in your brains, but I made sure we went over and over and over again that acceleration didn't depend on mass, right?
No, but Galileo was like.
And the reason why I made sure that acceleration didn't depend on, you guys know that acceleration doesn't depend on mass, is because of what we're learning today. So what we're learning today is a justification for that, which I think is kind of cool.
Can we go back to watching some
No, we had fun though. All right, so what about a mass of m?
Mass of m. What?
The big M?
Yeah,
It's one, right?
if I were to do this with a mass m, so just any old m, okay, and I want to find the acceleration, what am I going to divide this force by?
Little m.
Little m, right? I would need to divide this force by little m, wouldn't I? Yeah? So if I take that equation and I divide it by little m, so we have F equals 6.67 times 10 to the negative 11, 5.97 times 10 to the 24th, m over 6.38 times 10 to the 6th plus 1 squared. I'm going to divide this by little m, right? That's the mass of the masses, isn't it? That's the mass of these things that have been falling, right? What happens now?
You get acceleration.
We'll get acceleration, won't we? So F over m, that equals acceleration, right? So if I take this equation and divide by little m, what happens to the little mass? Cancels. Is there any more little mass in that equation? No. So what this shows us, Rex, and this is that justification I was talking about, what that shows us is that acceleration only depends on 3 things. The acceleration due to gravity depends on 3 things. What are those 3 things? What's this?
BG.
Big G. Right? What's this?
Big M.
Big M.
Big M.
Mass of the Earth or mass of the planet, mass of the sun, mass of the moon. Whatever big object you're standing on, that's big M. Okay? And what's this right here?
Radius.
The radius squared, right?
Could radius, could Big M be like a table or something?
It could be, but the acceleration would be very small. There's actually a Family Guy episode where Big M is Peter Griffin. Okay.
Oh,
And later on we'll calculate how big Peter Griffin has to be.
oh, you talking about
We
like
talked
the
about
orbit?
Yeah, when he has the apple going around. Yeah, we'll figure out how big he has to
I
be.
think
later.
TV around the time.
All right, so what this means, guys, is that the acceleration due to gravity. And Rex, I know you know this from earlier. Okay, what we've now proven is that the acceleration due to gravity does not depend on the little mass. It only depends on the big mass.
Big Mac.
Okay, so that proves Galileo's observations. That proves your observations. All right. So it's not just an observation now. This is something we've proven using theoretical physics. You want to spell theoretical physics, Rex? Because we didn't do any observations, just the calculations. Okay. Does that make sense? Any questions? So this A right here, we can rewrite it with a G. And that G means acceleration due to gravity. And what we calculated earlier is if we're on the surface of the Earth, that acceleration due to gravity will always be 9.78. If you don't believe me, then go through and multiply these out.
So G is always going to be the same for every single equation that we do.
Big G? Yeah, big G is always 6.67. Okay.
So I'm going to guess that we're going to have to like find the mass of things at one point.
We can use that to find the mass.
And the
You're right.
radius.
All right, are there any questions? Any questions? No? Okay. Let's try some examples.
That's all I have for you guys today.
I have 15 minutes left. I have a quarter of my hour left.
Okay, but
Oh
you
my
just think
That's like ending your basketball game at the third quarter.
Why do you always have to bring up?
That's like if
Examples
we're
from
tied
my
in a
life.
football game in the fourth quarter.
They don't have a mercy in basketball?
Yeah, it's all
No, like,
Yeah, the clock is immersive.
Yeah, but they just have a running clock, but they don't cancel the game.
They should.
It's not like it's not like baseball.
Has there ever?
How many
Have you ever been
running
coaching
backs
and like say Kellogg'sville got a running clock and then the team came back and
I
won?
sent some
What's
sleep
the
this
mercy
year,
in
y'all.
soccer?
Has that ever happened?
I like to sleep this
I
one.
think it's 8.
That's possible, though, right?
Why'd you unplug that?
How would you lose 8 by in soccer? That's kind of bad.
Yeah, well, it happens.
What about
Is
baseball?
that even possible?
Yeah.
Okay.
It happens.
I don't know.
But, like,
I think that's why they have a running clock because it's not possible at that point. And if we're up by 35 points, then we should be taking
I
that
don't think
down.
we ever got mercy.
Isn't it like 25?
No, 35 is football. Where's my eraser? So we can't go even worse.
Do you remember
Okay.
mercy in fall season? I don't think so.
Guys,
I think against Cowboys.
example 11. Mars has a mass of 6.42 times 10 to the 23rd kilograms and a radius of 3.4 times 10 to the 6th meters.
How do they measure that?
What is the acceleration due to gravity
How
on
do
the
they?
surface of Mars?
How do they measure the mass?
Okay.
Do they just put like
We're-
a scale under it or something?
No, we're kind of working backwards from the way you measure the mass of a planet. All right? We're getting there. Okay? I know. And the reason, the way we're getting there is because this equation right there, big G M over R squared. What's the M in this? The mass of the planet. So there's a way that we can actually figure out the mass of the planet. We're going to keep going on. We're going to have to actually combine this with the centripetal force ideas. And then we'll be able to figure out the mass of the planet.
How do you figure out the radius, or how did they figure it
The radius is easy. They can actually measure the radius of a planet.
out? Like with a tape measure?
No, they'll use a radio telescope, which sends a radio wave to the planet, and they can send a radio wave to one end of the planet and then to the other side of the planet. And then when they reflect, they can measure that angle, and they know about how far we are away based on how long it takes a radio wave to go to the center of the planet.
That doesn't seem
And
easy.
they can use geometry to figure out the.
I know that does
Doesn't
not
seem
seem
easy.
It's called parallax.
You said it's really easy.
It is really
They
easy.
should be
Wait.
astrophysicists.
Okay.
From Green Lantern?
So they figure out they send a radio wave here, figure out how long it takes to come back, Send a radio wave there, figure out how long it takes to come back. All radio waves travel the same speed, so they know those two distances. Okay. And then they know the angle they have to adjust their telescope.
Oh,
So then, if they know this angle, then they can figure out, and they know these two, they can figure out that one using law of cosines.
It's kind of like how they figure out the epicenter of the earthquake.
Well,
The epicenter of the Earth?
Yeah, because they have to use 3 different points.
It's like triangulation. It is triangulation. Alright, so I want you guys to do example 11A. Give it a shot.
Once I'm done.
You're done?
Yeah.
If you're done with 11A, then try 11B.
Somebody just call me dumb back there, man.
They said you're done.
Where's look? I got the. Look at this. Look what I got.
That's your answer?
Yeah, that doesn't look too hot, does it?
No, your radius is supposed to be squared, and you're supposed to use the radius.
Oh.
You're supposed to use the mass, not the radius.
Wait, what?
Amanda, you stabbed me in my
You
leg
plugged
hard.
in a
messed
radius
up.
for M, not a mass, Kyle.
In my leg hard when I was sleeping.
What are you talking about?
You plugged in a radius for M. For the mass, you plugged in a radius.
How'd you do that?
I looked one way.
Confusing
and I didn't
you,
see
dude.
you. And I walked
For
next to
real.
you walking away fast. I was like,
Now, for
obviously
big
I'm
M,
sleeping.
when you put in meters, you put
You
kilograms.
grabbed me on this side and then you just walked that way.
I was walking casually.
Oh.
No, you were like,
Dang it. I do what I did.
I started walking fast and I was like, get up.
Pushing over the table.
Yeah.
Yeah, 1.7.
Somebody got agree.
don't give it to him.
I got a really long nose for them.
Wow.
Sorry, you had something better than that.
I did.
No, you did.
I was trying to lean to your back, but it didn't